So in this part of the video, I'd like to give straightforward proof of this, proving this function is homogeneous. It can be written as a degree one variable function in terms of y over x like this. If you look at the example and accept that mainly these examples are coming from the polynomial cases, this is by looking at the example, you're pretty convinced that this is going to work, but it's also nice to see how those property that's described, the defining properties, are used to establish something like this in general, not even going through the shape of the polynomials. So we look at this example again and see how we're going to approach if this strategy really works without even going through this polynomial case. So that was one example we looked at earlier. So the homogeneous degree 0. And at the end, what we had here is this. So what is the one variable function we're talking about? Is the one variable function is this one here. So where's this v squared came from? That's exactly y squared there. Where's v came from? That's exactly y. And v cubed here came from y cubed, and so on. So that's main motivation. So let me summarize it here. We started with a something. Then we wanted to rewrite this whole thing in terms of y over x and see if that's possible. So we're going to call that as a v. Algebraically, we're going to turn this one into something only in terms of v. So that's what happened here. So that's only for this example, and that's what I'm saying is the motivation. So how are we going to do the next part? Here's some of a reasonable approach. We have this thing f of xy, and this is what we want. We're going to turn this one into only in terms of v. So first, if you write y as a x times v, you can easily turn that y into something in terms of v. So we're introducing v here. So the goal is that how do we get rid of x? And here's the magic, that this is a homogeneous equation. So now x became same scalar factor for this portion and that portion, that argument and that argument. So by the definition of a homogeneous function, if there's the same scalar function, we can ignore that same scalar. X becomes 1 in v. Now, if this two variable function is evaluated like this 1 comma v, you know this is one variable function. So we turn that function into one variable function. That seems like a pretty much proof, but here's how mathematicians usually state the proof. So let me show you the statement one more time. We're given this two variable function which is known to be homogeneous, and we have to show that there is this function such that g of y of x is that one. Okay, so they will first ask that, don't fool us or confuse us. First go in and give us a straightforward construction of this function g, and then verify if these two things are equal to each other. Okay, so that's what we're going to do. We're going to construct this. Logically, it's very clear if you approach that way. There is this function they're talking about, and we're going to construct it and then verify these two things are equal to each other. That's going to be the main outline of the proof. I agree that pretty much the proof, and that's how a mathematician like to outline a structure their proofs. So here's the first statement. How are we going to define that g of z? If you look at it there, and if you look at this part here, it seems like that part has to be, if the main variable I use something else, z, what is going to be the g of z? That whole thing must be f of 1 comma z, because they're motivated by this one. It's one variable here. If you look at here, v is exactly y over x, right? So that seems like the right thing. So that's definition, no confusion. Have two variable functions given. Ignore that x, make it into 1. Then use this second as one main variable. Then it becomes a one variable function, and that's our gz. Then you have to show this statement is true under this definition. So the first step is that you evaluate this function at y over x, and what this is, read this definition and see if you can algebraically show that's true. So wrote down over here, this is our goal, this is what we want to show. So next step is that we have this input y over x, so we're going to use this definition. So y over x goes to that part, and since f is given, and this is what we're having. So how can you turn this one into that expression? One trick is looking at this, we have to use a homogeneous property. So can we rewrite this one with the same scalar factor, right? Our goal is to pulling out this y, so why don't we look at this 1 over x as a scalar factor, like this one here. Then can we write this one with the scalar factor 1 over x something? Of course, this 1 over x times x is going to be exactly 1. Again, the motivation comes from, okay, this is our target. The right hand side looks like it has at least this part, so how can you get rid of that 1 over x? Using that property, the scalar disappears, this property of a homogeneous function. So I got this one, y times the scalar, so I want to write this one with that same scalar times something, and this is the only way. So here, that 1 over x and 1 over x, same scalar disappears, and we have f of xy, so we show that this is really that one. Or you can approach from here. Why don't we start from here, see if you can manipulate to that shape, and that's what we're doing here. F of xy, we're going to that part, and g of x looks just like this if you plug in y over z. So how can I pull out y over z? Maybe we should get rid of this x in there. So if you decide to make that x as a common scalar factor, and then it's going to be x1 and x and y over x must be there, so that is same as y. So x is a common scalar factor. That disappears, so that is just a 1 and y over x, the property of a homogeneous function. And there, by definition, this is exactly g of y over x. So that proves that there is this clearly defined function right here, such that this property holds. That was the statement of the lemma. So here, very nicely, we didn't use any polynomial, anything, just the property of a homogeneous property. You can deduce something like that. And this was quite clear with actual polynomial example. By doing this homogeneous equation problem, you might have felt that you're kind of repeating the same procedure over and over. They must be some sort of formula so that you can just directly go to that part, and that's what we're developing here. So if we have a homogeneous degree of n here, and it must be the same homogeneous degree n, so that's together, if you write it as a standard form, y prime equals something, then it's gonna we're gonna have a quotient of these two that'll result in homogeneous of degree 0. But right now this coefficient degree n, the same degree n, not necessarily one variable. That's why it's not separable. So that's the typical situation for homogeneous equations in differential form. So let's proceed with what we've been doing. So again, we're looking at this as x and y as a dependent variable of function t, and we are rewriting this one with y over x. So y over x is called v, and that's the technique they introduced for the homogeneous cases. V equals vt, that's a function of t, and y is replaced by this x and v. So this y part is replaced with xv, and this y part here is replaced with xv. And that y part, the derivative of y now, is the derivative of x times v, so we're going to apply product rule to that part. This next fun part is what this homogeneous property. Now, because of this substitution, x became a common scalar multiple of this argument of this function f. X became the same scalar multiple for the arguments of this two-variable function g. So this will factor out with the homogeneous degree x to the n, and will be the same over here. So x to the n factors out, so after you factor out, this becomes 1, and that part becomes 1. So now that's one variable function, and that's one variable function. And this x to the n will cancel, right? That's in general always happen. In this part, we apply the product rule because x and v is functions of t and multiply to each other. The shorthand notation without t, that is v dx and x dv, derivative x and derivative v. So that's the part. So let's put this dx and dv together, but let me introduce abbreviation of this one variable function, and that f bar and g bar. So we're going to write that for convenience. That's going to be one variable function fb, and g bar v. So with that, these are the one variable. Now if you collect dx, that's this part, and x to the n is cancelled, so it's fb bar. Here's dx, they have v and g bar v, so v times g bar b. And this is the only term that has v in it, so it's x times g bar b. So we're almost done. This is one variable, and that's one variable, and multiply by one variable, so it's easy to separate. If it's addition, we're again in trouble, but it's multiplied. So I will divide both sides by this one. That puts that one in the denominator. Both sides by that one x. That put this x in the denominator. So no matter what, you will always have this 1 over x in dx. That's a fast way to go, but you have to memorize a little bit. If you want to go quickly to here, this g divided by f plus vg. It has to be bar over here. So that part's simple to memorize, but not so much in this part. Well, that would be the formula. So if you have general homogeneous equation, and you can just go directly here to get the answer.